Thank you for the introductions and thank you for the invitation to come and present today. I'm very pleased to present with Rowena, and I'm very glad to say she's got the lion's share of the talk, so you won't be seeing too much of me. Okay, so just a little bit about IEAGHG, just a disclaimer. We are recognised as the IEA Greenhouse Gas R&D Programme, and we're a technology collaboration programme under the IEA. So our views are separate from the IEA, although we're organised under them. So our views are separate. So that's what you need to know there. As I said, we're a members-based organisation, 37 members currently, I think, from country members, governments, and companies. And I won't go through all of our activities, but primarily we commission around 10 technical studies per year, and we've been going for over 30 years. So we have a resource base of over 370 technical studies and reviews on our website, which are accessible there and are free to download to public. They're initially available to our members. So if you're either part of one of these companies or even if you're within one of these countries, you have access to our resources. We also organise a number of events, and we have a couple upcoming this year. Just to let you know, the 7th International Offshore Workshop on CO2 Storage will be held this year from the 16th to the 18th of September in Port Arthur, Texas, which will be free to attend, and we'll have an online capacity as well. And we have GHGT 17 in Calgary this October. Okay, so back in 2010, IEAGHG did a high-level review of geothermal energy and CCS. And since then, there's been a great expansion in the variety and maturity level of new concepts. And I think Jasper gave you a real flavour for one of those, which I think he said started in 2011, so since that review. So we felt it was high time to do another such study, and we commissioned the BRGM to do this work for us, which was to sort of provide a really dispassionate review of the different technologies where there's a potential for combining these two technologies. So just to give you a scale of geothermal energy in 2023, produced around 16 gigawatts. We've seen about a 4% growth per year over the past 10 years. And in IEA net zero 2050 report, the forecast was that geothermal capacity needs to reach 126 gigawatts in 2050. And like other renewables, it can provide stable contribution to the electricity grid. So combined with CCS could be a powerful tool. So basically the objectives and scope of the work which we asked BGO to perform was just to look at the type of hybrid CCS and geothermal systems that are operational or that have been provided in the literature. Some of these are just desk-based studies, so it was just to get a sort of scope of what was out there, what was being reported on, and what main criteria could be used to compare these systems. So what are we looking at in terms of their operations? And then also to look at what regions have the most favourable features for future implementation of these technologies. We're not going to talk about the mapping exercise in this talk. So this was broken down into a literature review and screening methodology, which Rowena will talk about. So just in terms of outputs, we've published the report. It's on our website, and there'll be a link to that later on in the talk. It comes with a set of appendices, which Rowena will describe, which are really have done an excellent job of bringing all of these technologies together in a very visual way, and also an Excel spreadsheet. All of our reports are peer-reviewed. So it's been through 7 experts in the field and then revisions so that the publication has been peer-reviewed. We've had quite a lot of interest in the report prior to open publication. It was published in August 2023, initially for our members, and then it's now publicly available. We've done a webinar on it, so if you are interested in some more of the details, you can go on our YouTube channel and watch that. It's about an hour long, so it's a little bit more in depth. And we've had quite a few views on that and some presentations on conferences, and there's a review paper in preparation. So I'm pleased to hand over to Rowena for the meat of the talk.
Thank you, Nikki. Thank you. I just want to point out that I'm presenting today on behalf of the BRGM team, my colleagues that are on the slide here. The context, a little bit of flavour. Geothermal energy has been combined with several other technologies over recent years, and we've seen a drastic increase in this. As Nikki said, this is the mixture between geothermal and CCS, and this means synergetic use of the subsurface. It also means added benefits that can be either environmental or revenue. Nikki's already talked about the objectives, and I'm only going to zip through the literature review and then the screening methodology. So the literature review, we defined 15 concepts that fell into this category and classified them into 4 different categories that I'm going to show you quickly. We also noted down any major characteristics that the concepts had, and you'll see why later. So the first one is the use of supercritical CO2 as a heat vector for geothermal exploitation and or energy storage. That's the one that the CPG is into. Second one is water-driven geothermal heat extraction. The one on the left is tending towards geothermal production, whereas the one on the right is tending towards CCS. We then have a category of other synergies. This might be, for example, the two CCS and geothermal working independently but in the same reservoir, and other borderline concepts, but we certainly don't have time to go into that today. So you can see the categories up at the top here again with the colour scheme. And don't panic, this is the 15 concepts that have been identified. But my job today is not to go into the detail or technical detail of each concept. It's literally to try and give you a flavour of the framework that now exists to be able to clarify a little bit better this complicated landscape. It's worth saying that many of the concepts are still in a very early development stage. Some are still only at the literature stage, whereas others have moved on to pilot. So just to give you 2 very quick examples of what the concept descriptions look like after the literature review. From 2.2 category, which is the CO2 dissolved concept developed by BRGM since 2012. But what I want you to notice is that each concept has an infographic visual aid like this one. And the legend is standard, so that each concept you see in similar characteristics presented. So here we're dealing with a conventional geothermal doublet. The particularity here is that we're injecting CO2 into the brine to extract heat, and the CO2 is in dissolved form. Because the CO2 has a solubility limit in the reservoir, it means that the amount of CO2 that we can store is limited too. So this is particularly adapted to small industrial emitters, no more than 150,000 tons a year. Sorry. So moving on each infographic aid, we also have information about the reservoir rock. So here it's sedimentary, porous and permeable hydrothermal reservoir. It talks about what the CO2, what form the CO2 is in. It also gives us information about the trapping mechanism. Here it's solubility and then mineral. We have information, graphic information about the where the CO2 comes from, the infrastructure that's used. Moving on to the left, we get an idea of the range of temperature and depth. Here it's quite low values compared to other concepts. We also point out the advantages and the limitations and an idea of maturity of the concept. One big advantage of CO2 dissolved is that we're bringing a solution to local, small-scale, hard-to-abate emitters. Another advantage is also that CO2 being in dissolved form, we avoid the problems that can be related to the buoyancy effect with supercritical CO2. One of the limitations is that it has limited individual potential for CCS. On the other hand, the replicability potential is high. So in terms of maturity, CO2 dissolved, we're looking to move towards the pilot scale. There's industrial companies that are interested in France, and there are potential sites that have already been identified. On the right-hand side, we have an idea of the services provided, i.e. the capacity in geothermal production or in the quantity of CO2 stored. There's also an index services ratio that shows how much geothermal compared to CO2 storage, and some idea of the implementation complexity. I can see Suzanne with her phone, so I'm looking at the time, so I'm going to hurry up. I want to show you, for comparative purposes, a second example. So that's from the first category. I purposefully haven't picked the one that you did, Jasper. So CO2 EGS enhanced geothermal system. And we can immediately see the use of these infographics for being able to compare the concepts. So here we're dealing with supercritical CO2 injected into a fractured reservoir at a deep depth. The aim is to use the CO2 as a working fluid to produce electricity, geothermal energy that is then generally electricity. Sorry, too quick. What else can I say? Yeah, the advantages here are the outstanding performances that can be done with this. The efficiency is much higher with supercritical CO2 as a working fluid than water, as Jasper explained. The limitations, though, are high investment cost, high development risks, a tricky design, and then, as I mentioned, you need a very tight proc with supercritical CO2 in a fractured reservoir. In terms of maturity, this is still at the literature stage. There has been some modelling, only of case studies. And as you can see on the right, I've already talked about the outstanding performance, but the values are significantly high, and the implementation is rather complex. So on to the second part, the screening methodology. We created a set of key performance indicators to apply to each concept. Then we established an analysis grid for comparing the concepts and their actual expected performance, and adopted a qualitative or semi-quantitative scoring of the key KPIs. The major outputs of this part is the Excel file and a set of further infographics where instead of doing per concept, we put all 15 concepts onto one graph. So the Excel file, I'm not going to go into detail, but it's just to show you well, how detailed this study is and the amount of information that's in there. You have the 15 concepts along the top, and down the side, you've got the KPIs that are actually into themes that we've addressed. So like ambitions and replicability, how much impact is this going to have on climate change, integration into an existing system, for example, but we also look at readiness and environmental impacts, etc. Down at the bottom, there's a little legend on how we scored each one. It's on a scale of 1 to 5, 5 being the best performance. This is completely objective. It's only done out of the literature and the data that we had in our hands. And then the beauty of this Excel file is that the user can take it and according to what knowledge he has or what site information or data he has, he can put this into the Excel file. So we're providing a framework for him to be able to consider one or the other technology or a group of technologies. The results at a glance. Again, the color coding up at the top with all the concepts and down the side, the key performance indicators and the scoring. I've just zoomed in on 3 concepts haphazardly to show you what it looks like. For example, the carb fix and the Clarke one have really quite high performance scores, apart from ambitions and replicability, but that's because they demand very, very specific geological criteria to be able to deploy them. So a couple of examples of what it looks like when we put all 15 concepts onto one plot. This is an overview showing down the vertical side the CO2 storage capacity, and along the horizontal the power capacity of geothermal exploitation. The grey ones are the end members for storage and exploitation. This one is a comparison of concepts on the CCS geothermal energy scale. So we're moving from 100% storage through to 100% geothermal. We've packed a lot of information into here. It's not just the 15 concepts, but it's also the pie charts down at the bottom. Give us an idea of the services that are provided. But not only the services, the pie chart also gives us an idea of the quantities. And I talked about CO2 dissolved earlier on, and we can immediately see that this one is small quantities, therefore aimed at small emitters. So the conclusion, it's the most exhaustive summary of hybrid geothermal CCS concepts to date. We've learned about the literature review and the methodology for comparing them. But why did we do all this? What's the importance of it? How can this be of any use? Well, it clarifies the landscape of recent or upcoming hybrid concepts. It enables a framework where we can actually compare the concepts, despite the fact that the data in the literature it can be really quite heterogeneous. It gives a framework for people's own needs, depending on what they're aiming at and if they have extra site data, for example. And this helps in decision making. It helps highlight the concepts with higher potential for deployment and therefore prioritize funding. And it's also a first step towards considering these concepts in future decarbonisation plans. So I'll just one last slide for Nikki to wrap up with the key messages.
Oh, sorry, not too far. Okay, so just a few key messages that really drew out from the report. So hybrid use of subsurface to produce renewable heat electricity could largely be decarbonised with CCS of an external industrial CO2 source, and it opens up promising solutions. As Rowena has described, key criteria have been identified and used for comparisons between concepts, and looking at total CO2 stored, energy produced, readiness, and subsurface features. Some of the most ambitious concepts in terms of high energy delivery and high CO2 storage potential include CO2 EGS. So there's lots of acronyms with this. BRGES, Earth Battery, Hybrid Energy Systems. They rely on high technological complexity, and they need to be proven to confirm feasibility. Whereas the sort of lower capacity systems like the water-driven geothermal concepts with CO2 reinjection have the advantage of using simpler and more mature technologies, making technical feasibility more likely to be achievable or already proven by existing demonstrators. So future work on the economic evaluation will need to accompany pilot projects to assess the economic feasibility. And that's been lacking in many of these desk-based studies to date, but obviously there's progress made and it's being pushed forward, for example, by Jasper. And engagement across multiple stakeholders are necessary to move the concepts to development. Obviously, public perception's been mentioned. Regulation, obviously, CO2 storage comes with its own regulation, so this adds more complexity to the system. So thank you very much for your time today. That's